Let's do it. It's go time.
Welcome to Go Time, your source for wide-ranging discussions from all around the Go community. Find us on the web at gotime.fm, on the Fediverse at gotime, at changelog.social, and on X at gotimefm. Thanks to our partners at fly.io, the home of changelog.com. Launch your app as close to your users as possible. Find out how at fly.io. Okay, here we go.
What's up, friends? I'm here with two new friends of mine from Speakeasy, Sagar Bachu, co-founder and CEO, and George Hadar, founding engineer. So for the uninitiated, Speakeasy takes care of the entire SDK workflow to save you and your team significant time, delivering enterprise-grade SDKs to your customers in minutes. You can generate best-in-class SDKs in TypeScript, Python, Go, Java, C#, and even PHP. So, Sagar, what's your excitement level for APIs and this API world we're living in?
I'm super excited about APIs. I think we went through Gen 0 of the API first revolution, and I think we're actually going to a second one now with the tailwinds of the AI ecosystem kind of causing that to be reinvigorated. So yeah, super psyched to be working in this space right now. I think everyone's at a point now where everyone knows about REST APIs and GraphQL APIs and gRPC APIs. And now I think we're actually getting into the second phase of that, which is how do people ship great developer experience in addition to the APIs? And how do we build like truly best-in-class APIs that turn into long-lived infrastructure? Right. This is kind of the vision I think that Stripe helped manifest for everyone in the fintech space, which is an API that really sets the bar for developer experience, but also like it's something you can truly rely on. Right. It's a true. If you make Stripe a dependency of your company, you can feel confident doing that. And I think that's the part of API development that really excites me.
I agree. That is exciting. So, George, teams who leverage Speakeasy are those who have leaned all the way in on documenting a solid open API spec and mostly want to be hands-off of their SDKs. Is that right?
Precisely. So you're coming to us because you want to be hands-off from that process. You want to put all of your effort into documenting your API, and then you're trusting and relying on great quality tooling to turn that into code and documentation, which is what we're doing for you. You're not meant to change or edit the code because it will be regenerated the next time you change your open API. So you ultimately put it in our hands. Once you've committed the changes to your open API, it's off to the races, and you get a new release of your SDK. You'll get a pull request to review. You will have the opportunity to look at the contents of the code, but quite often you can let it hum along creating SDKs for you or new releases of your SDK every time you change your API.
Very cool. Well, the thing that got me with Speakeasy that really helped me understand it was that, as George said, it is hands-off. You can just focus on documenting your API via the open API spec. And you still have pull requests, you still have visibility. And in fact, they will even hop into pull requests with you to triage any sort of anomalies or issues that come from the SDK generation and improve the back end of Speakeasy to make future releases better for you. I think this is so cool for teams who want to just be hands-off of their SDKs and focus on their product, focus on the core documentation around the open API spec, but still have all that awesome visibility. Okay, so the next step is to go to speakeasyapi.dev. You can start off with one free SDK. That's so cool because you can go there right now and try it out completely free. One free SDK. Let them know the changelog sent you. Let them know JS Party sent you. Once again, speakeasyapi.dev.
Hello everyone, and welcome to another episode of Go Time. My name is Natalie, and I'm here with Jesus. Okay. Jesus Espino joining us from Mattermost, and you are here to talk about the aha moments you got from reading the source code. Have you been doing Go for long?
Yeah, I've been doing Go for around 7 years already. So yeah, quite long. Not a lot. But
How did you start? Why?
Well, I started because I start getting interested in the language itself, I had a friend that she was learning Go and she was very excited about the language, and she shared with the cool things that you can find in Go. And I started getting interested. I started practicing, and actually I started contributing to open source projects. One of them was Mattermost, and like 6 months later, I started working for Mattermost actually. So it was a very, very good timing.
Nice. What language were you switching from?
I come from Python. I was using Python for around 10 years before that. So,
do you still use Python or completely all Go?
Time to time, I use it. It's a nice language also. I like Go more, but Python is a great language. And for very specific use case, I still use Python.
Like writing AI models.
Yeah, playing with AI is one of them. Probably some small scripting things, or maybe even some small REST API, very very small REST API with Bottle or Flask or things like that. So very small things, nothing big, but yeah, I still use it.
Nice. Let's start talking about the 10 aha moments that you got from reading the Go source code. How did that even come to be?
Yeah, well, this is I really like to know deeply my tools, the things that I use, the things that I work with every day, and things like that. In the past, in my Python background, I like to give talks and things like that, and get into the details. And back then, I investigated around how the Python objects works under the hood and things like that, how the different Python objects that were built in the language were working on, and all that kind of stuff. I prepared a talk. I did a talk actually in some conference about that. And then when I switched to Go, I start fresh. I didn't know anything at that level. I start to learn the language. I start learning the language and start getting confidence with it. And there was a point in 2020, 21 or something like that I felt confident enough to start investigating for preparing a talk. And one of the things that I investigated was exactly the same, how certain built-in objects works in Go. Mm-hmm. And where that objects were the slices, maps, and channels, because we're like the bread and butter of Go. So I started investigating.
Probably half the pop quizzes I'm seeing are usually around slices, arrays, and such. Yeah, that's a fun one.
Yeah, tricky, and understanding how they work under the hood is interesting. And that was my first attempt to start reading the Go source code in here and there. Was relatively targeted, so it was kind of simpler that time. I prepared a talk. I give that talk in the FOSDEM for first time. So what's really great, give me a lot of insights about how channels actually work and how slices and maps work, and even some small sneak peek on how Go routines works. So it was an interesting experiment. And that is how I started. Then I just keep going. I use conferences and public speaking as an excuse to learn things that I want to learn. So I prepare a talk, and then I have to learn something to the degree that I can give a talk and I can answer the questions that sometimes is really hard. So yeah, it's how I get into that. So the 10 aha moments come from the exploration that keeps going, preparing other talks that if you want, we can keep talking about it.
Yes. And also, already here, episode number 2, part number 2 of this one. Do you want to start with the first biggest aha moment? How would you go about that? The biggest, the most impressive ones, or the most chronologically, like the order of that?
Yeah, I think I like the chronological approach because it's kind of easier for understanding my head, and probably explain sometimes why it's an aha moment. And the first one for me is exactly about the slices, maps, and channels, and specifically about the slices. That was how slices are implemented under the hood. Because when I started writing Go, I was said that you have slices, and the slices are immutable, and then you just append things to that slices, and then you get appended version of the slice. The thing is, that sounds really, really inefficient. It looks like it has to be inefficient. How in the hell are you doing that to make it that efficient? Then you realize when you start investigating the code, you start realizing how they are doing it, and it's really smart. Slices are not slices, just a sort of pointers and counters. The real data is stored under the hood in an array, and that array is changing in size and is automatically managed for you. And the growing of the slice or the growing of the underneath array is not something like I going to add one. It's normally doubling the size of the previous array to store more data. And then because of that, you understand why you should be pre-allocating the array size. All that kind of stuff was one of my first aha moment, was like, oh, so that's the reason why it's efficient. It's really a smart approach, actually. Mm-hmm. Then you have some pitfalls that you know because you know how it's implemented under the hood, but there are some pitfalls around that approach, that is using multiple slices that points to the same array, and one of them get resized. Were connected before because we're accessing the same underneath array, but suddenly they are not connected anymore. So it's kind of a weird behavior that it's unexpected, I guess, if you don't understand the implementation details. But yeah, that was my first one. My first aha moment was like, oh, then that is how they make this efficient and make this work smoothly. So,
were you comparing it to what you know from other languages, or was it more like, this is the first time on that for arrays I'm focusing on how is it done under the hood?
Yeah, I think from Python was very similar. It's not the same because in Python, I'm not 100% sure. In Python, they are not appending things. You are saying, hey, I have a list of elements and I'm adding things to that list. So semantically, you are understanding that you are adding things to that list. Under the hood, if I recall correctly, is pretty similar. The behavior is just an array of memory that keeps doubling, and you have this pointer and these counters that give you the length and the capacity. All that is almost exactly the same. If I recall correctly, I don't have the Python implementation very fresh.
Yeah, of course, it's been we're not talking about the focus of Go of Python source code. I'm just curious if you generally were focusing on the same topic for other languages, or was Go kind of where you started really diving into this?
No, I start in Python before, and then I started with Go because I was using Go every day. So the whole point was, it's a tool that I use every day. I want to understand it better. That's the reason why I did that in Python before. I want to do that with all the tools that I use. I did that with Git in the past. I want to do that with Postgres in the future. But yeah, it's something that I want to do. I don't know if I'm going to do it. It's a matter of time, and sometimes it's hard to find the time for that. But yeah.
Yeah, it's like an advent of diving into code can be a fun project. Instead of solving challenges like in advance of code, actually reading somebody else's code and learning those things.
Yeah.
New Year's list. Yeah.
Yeah, it's challenging. I have to say that Go helps a lot there. Go is a great language to read because it feels like home everywhere. Of course, the algorithms and the complexity of the different projects, it's different. And reading a compiler source code, it's a tough thing because it's a compiler. The complexity of a compiler is already big enough to be challenging. But at the same time, you see the same kind of styling everywhere. The code it's kind of familiar. Okay, this is an error. If error, whatever, then nil, whatever. All that things are kind of the same. So it feels less weird than other languages where every project has its own styling.
Yeah, very much goes to our human need for pattern recognition, for sure.
Yeah, exactly.
I agree. Okay, so you say that the arrays implementation was making sense and was a little bit familiar, also speaking to your pattern recognition as well.
Yeah. So no, I was interested in that at the end of the day, most of the implementations, so for example, slices and maps is not like super weird implementation. You can find very similar implementations in other languages. It's just a relatively standard implementation of certain things. There's details on for example, maps that can be different than other languages. For example, in Go, maps keys are unsorted and are unsorted on purpose. Actually, they are unsorted on purpose up to the level that every single map have a random seed for the keys. So it's two different maps with the same keys and the same values are going to be ordered differently. So it's on purpose, it's by design. But at the end of the day, most of the languages have its own implementation of these kind of things, and most of them are kind of similar around hash maps and slices and all that stuff.
Okay. How about the second aha moment?
Okay, next step. One of the things that I was intrigued about Go, because it's one of the key things, is Go routines. It's something that everybody wants in Go, everybody loves in Go. And I did want to understand better what a Go routine is and how it works. And I started digging into the source code and I started investigating how the Go routines works under the hood from the perspective of the Go routine, of the life cycle of the Go routine. And actually, for that, I prepared another talk that is called The Sacred Life of a Go routine. And in that talk, what I try to do is follow the process of when a Go routine is created, how it's created, and what are the steps that the Go routine goes through, and how it changed from one state to another, and what are the reasoning around that changes. And one of the things that I discovered while I was doing that was it's something that I already have the kind of the intuition around that, or the understanding about that is Go routines are cooperative. But whenever I start seeing the code, was more obvious and evident that it's a cooperative approach. In threads, in operating system threads, you have the operating system deciding when to cut something and assign another thread to the processor. In Go, the Go routine itself is the responsible of saying, hey, I have to stop, I'm going to stop myself, call the scheduler to select another task or another Go routine, and the Go routine is going to start running. Not only that, the Go routine, I stop myself because I'm waiting for something, and the one that is going to wake me up is another Go routine. For example, whenever you send something to a channel and it's another Go routine waiting, you are going to wake the Go routine that is sending to that channel is going to wake up the other Go routine. So they are collaborating together to do all the processing. There's some special Go routines like the system monitor Go routine that is doing certain things, or the net pool that also it's kind of monitoring certain things for getting back that Go routines whenever they finished. But in general, the Go routines are waking up each other or are sleeping by themselves and calling the scheduler to select another Go routine. So that cooperative nature of the Go routines is something that I found very interesting and was an aha moment for me also. Yeah.
So you said the previous one, the arrays one, made a lot of sense. Does this one makes a lot of sense? Would you have done it somehow differently?
I think it's kind of a natural way of doing that whenever you are doing coroutines it's not exactly the same a coroutine that what Go's have, but it's this kind of cooperative approach where you have one single thread and you have to decide when to change to one or another. And it's just easier if you let the Go routines collaborate than if you have to put another process on top of that, orchestrating all of that Go routines. Because actually the Go scheduler is not another process, it's not another Go routine, it's nothing like that. The Go scheduler is a chunk of code that the Go routine that is going to sleep, or the Go routine that finished his work and is going to go to bed, it's going to call the scheduler code, and the scheduler code, it's going to transfer the execution to the scheduler. The scheduler executes and selects another coroutine and transfer to that coroutine the execution. So it's just a chunk of code that transition from one coroutine to another. It's pretty cool, actually. It's super interesting code. I don't know if I answered your question, actually.
Yeah. Another philosophical question, a little bit. As a background for the question, have you watched Rick and Morty? Do you know the concept of Mr. Meeseeks?
Oh, no, I don't. Sorry.
So there is a concept of a little blue creatures that is called Mr. Meeseeks, and I found it super helpful to understand this concept, also of like spinning up a task that has to do exactly one thing and then it dies. Mm-hmm. I think probably there's some developers and the creators of the show, because I found lots of similarity. And then when AI came, and the concept of agents, autonomous agents in the world of AI, not the world of software, it's also a little bit similar in the sense that AI agent gets a task and then it spins off subtasks and then it finishes the task and kind of bubbles up to report. So I kind of see similarity between the three of them. And I hope that in those 2.5 sentences I explained enough of this logic to you. But this will be my guiding question kind of throughout our conversation on the aha moments, because I like finding lots of equivalence between our current day software and what I try to imagine AI-based software will be. So this is kind of, I don't know, you're not familiar with Rick and Morty. I get that. That's probably better. Have you played at all with AI agents? Do you have enough experience to say an opinion about this or not yet?
Not yet, actually. I haven't played. I don't know what you mean with an AI agent. So that's...
Autonomous agent is a better name.
Yeah, I guess it's something like you ask to realize a task and it's going to use external resources or external actions to fulfill the task. Something like that, I guess.
It basically the AI goes and decides what is the subtask. Like you give it a goal, it breaks it down to subtasks, and then it spins off mini AIs to execute those tasks, let's say, which is very, very similar to that concept.
Yeah. Yeah, could be. Yeah, no, I don't, it's hard for me because I like AI. I have used it, but I'm not very deep into that. But yeah, I think there's similarities at the end of the day. What coroutines are is just processes that are kind of independent up to a certain degree. They have a task, they have to realize that task, and they are kind of independent from the rest of the coroutines. There is actually what is something like, for some people it's weird, is coroutines doesn't have a parent, if I recall correctly. So a coroutine is a coroutine. There's no relationship with 3 coroutines. You can execute thousands of coroutines and they are not related to each other, not even with the parent or the one that spawned it. So I don't know. I think I'm a bit lost with your questions, to be honest.
Yeah. Well, it's even more like an opinion than a question, but just to confuse a bit more, and then we move on to number 3. Okay. Another similarity that I see there is also to the concept of threads in processors. Mm-hmm. I don't know how much you got a chance to dive into like operating system breaking down things into telling the different processors how they run around their tasks and so on. But there's also like now you have threads and so on. So it's also, I see some similarity in those concepts. And I personally find it really cool that it kind of goes between the different fields that have something to do with each other, but not fully. Yeah. Just an observation. It's not a question. If you have experience there, I'm happy to hear your thoughts. If not, tell us about number 3.
In threads and the difference between threads and coroutines or something like that, or?
Yeah. If you want to chat about that.
Yeah, well, now it's interesting how it's solved in the Go runtime. It's basically they abstract you from the operating system threads and call them CPUs, actually processors, actually, mm-hmm. And then that processors gets assigned to different coroutines, but the coroutines and the processors are not highly coupled, so they normally have certain tendency to execute in the same processor on the same operating system thread, but it's not mandatory at all for the coroutines. So mm-hmm. the coroutines can execute in different operating system threads. So it's a very smart approach that decouple the CPU and the coroutines, or the operating system thread and the coroutines, and allows you to execute at full capacity of your processors using that architecture. Because if a CPU is overloaded, you can take the coroutines from other CPU and start executing in the one that is more free, things like that. So it's very cool how Go abstract you from CPUs, operating system threads, and the coroutines. So it's pretty cool.
Yep, and efficient. So what is your number 3 aha moment?
Okay, number 3. Oh, well, this was a kind of silly one. I was investigating the compiler, and one of the things that I started investigating was the process for tokenizing and parsing. And whenever I start reading the parser, I just realized that it was obvious anyway, but I realized that whatever is in the parser, in the AST tree, is what you can have in a Go file. There's nothing else. So if you start seeing how the AST tree, the abstract syntax tree for Go, is generated, you are going to see that it's one abstract syntax tree per file, and it's going to have an import, a set of declarations, and a set of imports. And a declaration can be a constant, a variable, a function, and a type. And that's it. There's nothing else that can be in a file. So it was kind of a sensation of complete understanding of something. I say, okay, now I know where is the boundaries. So everything it's inside these boundaries. There's nothing else that can go in a file. So there's nothing that I'm missing. It's constants, variables, functions, and types, and the import and the package name. That's everything. And probably it's kind of silly, but for me was like an aha moment. So it was like, oh, that's it. Of course, then you have the body of the functions and all that stuff, and there's a lot of stuff that goes there. But yeah, inside a file, you only have that things.
This makes me think of how in C, I think it's in C, that you have the header file and you have the code file, right? It's kind of similar. Let's scope our little universe, but this is scoping it for that file, but it's kind of like knowing that this is everything that's included there.
Yeah, it's kind of like that, exactly. You have a clear definition of what can go there. It's not exactly the same because in the H file, you are saying, hey, these are the functions that I declare. It's kind of publishing. This is the public interface. But at the same time, is like, okay, yeah, if I understand the H file, in theory, I should be able to use it, and I should be able to understand all the boundaries. So yeah.
And you say that what you liked more than that, this is like defining, scoping it for this file. It's kind of scoping it for Go in general, that this is your entire toolbox and there will be no surprises. It's like not keywords, but toolbox, really.
Yeah, there's nothing else. If you think, oh, could I execute a chunk of code inside the main file, but outside the function? No, you can't. That's it. It's a variable declaration, then you can. It's a constant, then you can. But it's not that. It's not a type definition or a function. You can't. There's no representation for that. You can't represent that in the AST. There are the pragmas and this kind of, but they are comments that are handled in a smart way. But at the end of the day, the AST is just that. There's nothing else that you can represent with that.
Sounds like it has not been a talk yet, this aha moment.
Not really. There's a talk. The aha moment comes from another talk that I was preparing, actually. That was at the time I was preparing the Understanding the Go compiler. Actually, it was called Hello World from the Code to the Screen. I prepared that talk. I did that talk in the GopherCon US, but then I made an updated version to the last version of the Go compiler for GopherCon UK, and I renamed that to Understanding the Go compiler because it was more clear, the title, and I don't want to mislead people around what I'm going to talk. But yeah, it was on that understanding the compiler, and I go through the whole compiler, and there's a lot of aha moments that comes from that talk, because I went through the whole process of compiling, and the idea was I have a hello world, and that hello world is going to be the main character of my talk. Is going to go through the whole process of transformation until getting to a binary. And I want in the talk I guide you through the whole process, and that's the idea. And this aha moment comes from that, and there's some that come from that too. So if you want, we can jump to the next one. Actually,
yeah, let's do that. So aha moment number 4.
Yeah, I think so. When I was investigating that, one of the things that I investigate during the process were 2 characteristics that were escape analysis and inlining. Mm-hmm. And the escape analysis, for that people that doesn't know that, escape analysis is a process inside the compiler that is going to decide if a variable needs to be stored in the heap or can be stored in the stack. So that decision is made through escape analysis that basically decides, hey, if it's possible for me to use the function stack to store this data, or because the scope of this variable escapes from the function, I need to store somewhere else. That means basically the main memory, the heap. So that is what escape analysis does. On the other hand, you have inlining. Inlining is a process that analyze a function in the co-compiler. It's a process that analyzes the function and decide if the function is simple enough to be embedded, to be inlined in the other side, in the call side. Instead of calling the function, you are going to take the whole code of the function and replace the function code with the code itself. That is inlining. And it depends on the complexity of the function, that it not necessarily means the size of the function. It means the size of the function, but also means the operations that you use inside the function. So the cool thing that I learned was, if you have escape analysis that decides a function needs to go into the stack or the heap, and you have inlining that allows you to take a function and put the function in place of the caller, what is going to happen is they are going to collaborate together. So if your function is simple enough, it's going to be in line, and suddenly the scope of your variables is bigger, so it's more probable that you can use the stack instead of the heap. So that was very cool. That was very interesting. It's something that I found super interesting. Yeah.
And what did you have any chance of implementing this function, like writing code that is kind of corresponding to this functionality that was extra efficient or interesting, or
not
or
really?
Is there a use case you can imagine for this to be interesting? Or because as you were describing this, I had nothing come to mind.
There are use cases. I think you have it's a tool that you have there, and sometimes you can say, okay, I have a very tight function here that is generating a lot of allocations. Then I can try to tweak that to reach the point where this gets in line. So that's one option. But also, I think the cool part is knowing that you can make decisions that are just smarter around creating your structs. For example, if you have a new function for creating a new struct and you have an initialization process inside that function, that new function almost for sure is not going to be in line, because the initialization process is going to get complex enough to not get embedded, to not get in line. So the scope of that variables is always going to be, whenever you execute new, is going to return a pointer to that variable. And because of that, it's going to always go into the heap. But if the function is small enough, if you say, hey, the new function is going to create the object and return the pointer, suddenly the new function is always embedded, is always in line, and it's always stored in the stack of the parent, unless there's other reason for escaping. But you are storing that in the stack of the parent. And then if you call, for example, an initialization function, that initialization function is already working in the stack. So keeping your constructors small enough to get them embedded, or then inline it, it's going to be a good practice in general. So, for example, that is a good thing, because it's not going to give you a huge boost in performance, but it can get you tiny improvement in performance here and there, and suddenly you are gaining. Well, that adds up at the end. So yeah, it's
that makes a lot of sense. That would be actually super interesting to also run tracing on that, for example, and to compare.
Yeah, if depending on the size of your application, you can have thousands of creation of certain objects, and if they go to the heap instead of the stack, it's going to be a lot of allocation, a lot of garbage collector pressure, a lot of other stuff that maybe is not that important. So,
or actually, we'll find big differences. I would be very curious. We do have a tracing episode in planning, part 2 of that. So that will be. I will remember to do a cross and to bring this up there as well. It's a cool observation.
Yeah, actually, I think the inliner now, it's being rewritten. I don't know if it's already finished the work.
I think in 23 it will be released in the updated.
Yeah, with the profiler, right? With the profile guide optimization. So yeah, that can be very, very cool to see if that is going to have a huge impact, because probably it's going to have certain impact there. Yeah.
Anything else to say about point number 4?
I don't think so.
Okay.
We have a lot of field to cover still. So.
All right. Jumping back, and we are continuing now with aha moment number 5 and 6.
Yes. The other thing that I was doing, well, I keep investigating the Go compiler and go through different steps in the process. And I reached a point that was super interesting for me. That was another aha moment. That was when the Go compiler gets machine specific. So all the process related to tokenizing, parsing, there's an intermediate representation in the middle. Then it's converted to something that is called SSA, that is single static assignment. And then it's apply a lot of optimizations. And there's a point in the process of converting SSA or processing SSA where it's applying optimizations, and at certain point, there's one of the passes of the optimizations that is called lower. That is the exact point where the compiler starts doing things that are machine specific. Everything before that point, it's machine agnostic. Is if you have an IRM or if you have an AMD 64, doesn't matter. It's all the same code base. And then gets into this lower phase of the SSA transformation or SSA passes, and gets converted into a machine-specific SSA. And then apply other optimizations. And finally, with that optimizations applied, start generating the binary, the linking, and generate the final binary that is an executable. But it's pretty cool that very far in the process, it's when you get the machine-specific part. That by itself was an aha moment and was very interesting for me, but I'm also a big fan of TinyGo. I love microcontrollers. I love playing around. I'm not good at it, but I love playing around with them. And for me, it was kind of interesting how TinyGo was doing that. And it's very interesting that TinyGo is follow a very smart approach. It's basically taking everything up to that point, everything up to SSA. It's up to that point is the same compiler, it's the same code base mainly. And in that point, it takes that SSA, and instead of converting that SSA into machine code, it's going to convert that into a LLVM intermediate representation, or LLVM kind of self-assembly. And then LLVM is the one responsible for compiling that to the microcontroller specific architecture. So Apart from that, you have to have a runtime that is compatible with microcontrollers, because in microcontrollers, you don't have the same kind of access to things. You don't have an operating system and things like that. But at the end of the day, the compilation part is exactly the same. So that is the reason why TinyGo is exactly the same language. You can have differences in the runtime, but you don't have differences in the language because it's the same one and it's leveraging that point. So for me, that was like, oh, wow, these people is really smart. So I really love that aha moment. And actually, I'm a big fan of TinyGo. So.
Shouting out to the cool things that TinyGo does. And together with Ron Evans and Daniel Esteban and the team who is working on the cool projects around that.
Oh, yeah.
Yeah, that is interesting. How would you say that this? So if this maps easily to across the different processors and it maps also to little tiny embedded tech, how would that be working on GPUs, for example?
Yeah, that's interesting. I think the GPUs have a different set of instructions, so I don't think it fits really well with that. Mm-hmm. The things, I'm not an expert, to be honest, but my sensation here is what you have is a pseudo assembly that is oriented to a general purpose CPUs. And that general purpose CPUs gets general purpose CPU pseudo assembly gets converted into real general purpose CPU like IRM or AMD 64 or things like that. So applying that to CPU, you can apply the same set of ideas probably. You can you can do what Rod Pike did here, that is, or what the Go team did here, that is taking generating a pseudo assembly that is going to be for GPU code and build that up to the level that you have this intermediate language. And whenever you reach that point, you convert that into the specifics of different GPUs assembly code or instructions. But I don't think it's applicable to execute the Go binary, for example, or a Go binary directly into a GPU, because I think have different set of instructions. It's not the same kind of machine that you are managing there.
Yeah, that's fair.
Again, I'm not an expert. Maybe I'm wrong here. So
it's a guess. It's a surprise question. Yeah.
Yeah.
Yeah, but that definitely is interesting, and I will go and look about that a little bit. I'm also now curious. You said embedded TinyGo, and although this connection has been around in forever, I'm kind of only now starting to think, how different will it be for FPGAs, for example, and like all the other hardware out there in the world. Maybe one day we'll do an episode about Go and different processing units. Yeah. Well, we only covered 6 of the 10, but we're slowly approaching our time, which means we will have to do a part 2, because you're just bringing up 2 interesting points and I have too many questions/comments about them. My last question to you would be, do you have an unpopular opinion?
Unpopular opinion. I actually think you should probably leave.
Okay, I think I'm going to get some hate for this. So that's what unpopular opinion is about.
Yep.
I think mechanical keyboards are just glorified nostalgia. So it's
loudly glorified.
Yeah, very loud. Glorified nostalgia. So that's the thing. I have used them. I don't think are more comfortable. I don't think are better. For sure, I'm not going to make you a better programmer or improve your performance or something like that. There's no way. I understand for some cases it's pretty cool whenever you are building your own keyboard or this kind of split keyboards or programmable keyboards that you have your microcontroller and things like that. For that kind of cases, I found that cool because you can have your switches and all that stuff, and there's a lot of pieces out there for doing that kind of things. But I don't know, paying 10x, it's all the 10x that you are going to get from a keyboard. It's 10x in the price.
And the sound, the noise.
Oh yeah, exactly, and the decibels. Yeah, getting that 10x in the price for something that is, I don't know. Probably it's an unpopular opinion. I get that the people that is going to consider this unpopular is going to consider this very unpopular. So let's see.
Well, I cannot say I don't agree with you. So at least with me, you are popular. My opinion is on the unpopular opinion is on a similar topic. Trackpads are better than mice.
I use a mouse, but yeah, I think so.
Well, I guess we both agree. Then with this consensus, I will say thank you so much for joining and sharing your interesting insights. And I am looking forward to episode 2. And thanks everybody who joined.
Yeah, thank you for having me.
That is Go Time for this week. Thanks for listening along. Subscribe now if you haven't already. Head to gotime.fm for all the ways, or simply search for Go Time wherever you get your podcasts. You'll find us. Hey, do you receive our changelog newsletter each Monday? If not, let's fix that bug. One reader calls it so good, he considers it a competitive advantage. Sign up for $0 at changelog.com/news. Thanks once again to our partners at Fly.io, to our mysterious beat freak, Breakmaster Cylinder, and to our friends at Sentry. We love Sentry. You might too. Use code CHANGELOG when you're signing up for a team plan and save $100. Why not, right? That is all for now, but we'll talk to you again next time on Go Time.